All right, we're going to try to solve this problem, 1360. At 25 degrees Celsius, the vapor pressure of benzene and toluene are those. A solution made by mixing this many grams of that and that many grams of toluene is prepared. And we want to know at what applied pressure and torr will the solution boil. So basically, what's the boiling point at 25 degrees Celsius? What's the normal boiling point? Okay, so hopefully we remember that this relationship is this is related to the mole fraction of the material. So the vapor pressure, or sorry, no, the vapor pressure, the pressure total of a system will be equal to the mole fraction of whatever contributor there is times the vapor pressure of X. Sorry, the vapor pressure of X. Okay? So what we're going to do is, and if there's multiples of these, mole fraction of B times the vapor pressure of B. So all we have to do is take the vapor pressure of A, 93.4, vapor pressure of B, 26.9, and we just need to fill in the mole fractions there. Okay, the mole fractions. So we have to determine how many moles of the benzene and the toluene. Just need the total number of moles. So benzene, we have 35 grams of benzene, 35 grams of benzene, and we want to go from grams to moles. The molar mass of benzene tells us there that chemical formula is C6H6. So we'll just get out our, well, I'm just going to get my phone because I'm lazy. All right. What's the molar mass of benzene? Okay, so that's going to be moles of benzene. Toluene, is that the other one? What's the molar mass of toluene? Okay, so 35 there. So I'm just going to find out the moles of benzene and the moles of toluene. So 35 divided by 78.11, 0.4481, 65 divided by 92.11, 0.7057 moles of toluene. Okay, so total moles, right? That, whoops, that plus that 1.1537, adding these together, right? So 1.1538 is the total moles, and then I can just take moles of benzene and moles of toluene over the total moles. I'll start off with the moles of toluene, the total moles. So 0.611 is my mole fraction of toluene. Just double checking that it's toluene is the 26.99, right? So 0.6116 is the mole fraction, right? Okay, now I'm looking for the mole fraction of A. I'm going to take my 0.4481 divided by 1.1538. Total mole, or mole fraction, 0.388. Okay, so there we go. So 0.388 times the 93.4 because that is the vapor pressure of the benzene. All right, 36.27 plus 0.6116 times the 26.9 is 0.6116 times 26.9. So that's 16.45. 16.45. 36.27 plus 16.45. 52.72. 52.7. So that's our vapor pressure, 52.7 for the mixture. All right, so we have 13.62. Benzene and toluene help achieve a good engine performance from lead gasoline at 40 degrees Celsius. The vapor pressure of benzene is 184, and that of toluene is 58. Different temperatures now, so different vapor pressures, right? Suppose that you wish to prepare a solution of these liquids that will have a total vapor pressure of 96 torr. What must be the mole percentage concentration of each of the solutions? All right, so this time we're saying we want something that has 96 torr, and we're looking for what our mole fractions are going to be of benzene and mole fraction of toluene, and we multiply the vapor pressure of benzene and the vapor pressure of toluene. Okay? So, the vapor pressure of benzene is 184 here, right? And the vapor pressure of toluene is, where is it at? 58. Okay. And now we could write these as variables, x and y, right? But if we do that, that would give us two variables, and we only have one equation. If we did do x and y, we could think what the relationship between x and y is. The mole fraction of benzene plus the mole fraction of toluene is always going to equal 1, right? So that's nice to know. So we could say that this is, maybe we could call it x, and this could be 1 minus x, right? So that we only have one variable now instead of two variables. And now it's just math. Hopefully we don't make any mistakes. 58 minus 58x, 184x, 96. Right? So I just need to combine my 184 and the 58 minus the 58. The x's together. So there's 126 plus 58 equals 96. 96 minus the 58. 38 equals 126x. Okay, so then 38 divided by 126, x equals 0.302. So then if that is my mole fraction of benzene, right, then 1 minus that will be our, 1 minus that will be our mole fraction of, that's mole fraction of benzene, mole fraction of toluene equals 0.698. Okay? And they have the question asking you the mole percentage concentrations. Therefore, this is going to be 30% benzene and 69.8 or 70% toluene. Okay, good. A solution containing 13.64. A solution containing 8.3 grams of some non-volatile substance dissolved in 1 mole of chloroform has a vapor pressure of 5.11 or 511 torr. The vapor pressure of the chloroform is 526 torr. So we want to calculate the mole fraction of the solute. the number of moles of solute in the solution, and the molecular mass of the solute. Okay, so this is the same scenario, right? We have the total vapor pressure equaling the mole fraction of, in this case, our chloroform times the vapor pressure of the chloroform plus the mole fraction of the unknown, UN, times the vapor pressure of the unknown. The only difference in this scenario is that the unknown is not volatile, so this vapor pressure is 0 at this temperature, and therefore this whole side cancels out, and all you have to worry about is the mole fraction. And if we know the vapor pressure of the chloroform is 511, we can solve for the mole fraction of the chloroform simply by the fact that they gave us the vapor pressure, 511 is the vapor pressure total, right? Vapor pressure solution, yeah. So this is the 526, which is the vapor pressure of the chloroform. So then we can solve for the mole fraction simply by taking our 511 divided by 526 here. So 0.971 is the mole fraction of the chloroform. Mole fraction of the chloroform. That tells us that the mole fraction of the other species is 1 minus the 0.97, right? And there's 8.3 grams of the non-volatile material in there, and there's 1 mole of chloroform. 1 mole of chloroform. So if this 0.971 relates to 1 mole of the chloroform, right? Then the mole fraction of my other material, which is 1 minus this value here, right? 0.0285. That's the mole fraction of our unknown. All right. So we have our 2 mole fractions there. And there's a relationship. The same mole relationship here relates to the molar relationship of the actual moles of material. So just like 0.97 moles of this for every 0.028 moles of this, because we're told that there's actually 1 mole of this chloroform, we can set up this relationship where there's 0.971 moles for every, the mole fraction is equivalent to the 1 mole of the material, 0.0285 mole fraction of the unknown, and we can identify how many moles of our unknown must be in our sample. So 0.971, no, wait, we start over. 0.0285 divided by 0.971, 0.02935. So the mole of our unknown is 0.0294 moles of unknown. The mole fraction is 0.0285. That's our mole fraction of our unknown. Okay. A is look for the mole fraction, B the number of moles, and C the molar mass. So if I know that they told us 8.3 grams of our material, and that must be contributing to the 0.0294 moles of the material. This is our unknown, right? So then we can take 8.3 and divide it by our moles of material, and that will be our molar mass. Our molar mass. Let's see, did I do that right? So dividing our mass times our moles gives us our molar mass. The thing that's interesting here is it depends pretty heavily on your significant figures, right? So here we carried 3 significant figures 0.0285, and if we rounded that answer to 0.029, then going into this answer, 0.029 moles of material, if we just put mole fraction here, if we took our mole fraction of 0.029, and then, let's see, 0.029 as our mole fraction, right there. If we round this mole fraction to 0.029 and then solve for this, we would get a slightly different number. And instead of getting 278, we might get something like, our calculator here, 282. But so it does get become kind of a sketchy thing to be able to predict. But taking your grams over your moles should give you your molar mass.